4 or 5 years, I'm not quite sure. Generally what I look at is energy efficient architectures and the way to productively design them. So somewhat my work is a little bit social science oriented, like how do I get people to be more productive. The majority of it is very sort of machine learning-esque. So instead of trying to get you to do your work, I try and get the computer to do your work for you. So there's some interesting things there. I've worked a good bit, been in school a good bit, seen a few things. I enjoy a lot of topics, so feel free to interrupt and ask questions. I'm a very careerist-oriented person, so I focus a lot when I'm teaching on how do you get a job in the area that you're trying to get a job in. So I kind of have a different focus. This sort of happens in year 4 or year 5 of your undergrad as the classes all of a sudden become very relevant to what you want to do. So maybe I can help fill in the gaps. So you're taking a class right now, you're going, why am I doing this? You know, I'm happy to answer those questions too. So what's the focus of the talk? What are the focus areas in the circuit specialization and who are the faculty? So this is kind of important because generally you're going to pick one of 3 specializations, and so this might be a way to decide. And then the faculty might inform like what sort of ultimate direction is good. So given that one faculty does this, maybe that area that they specialize in makes sense. What are the applications for circuits and the research we do at ASU? So the first part might inform what kind of job you get, and then the second part, the first part might inform what kind of job you get, but it also might tell you, am I doing something important, right? Because ultimately, we all like to feel that we provide value to society, and so this might be some way to get there. And then what sort of research do we do at ASU? This is kind of helpful if you want to get an idea of what advanced things are going on, but also where you might go to get more information. Or if you're interested in research or getting some job experience, those are the people who you would talk to. And then where do we ultimately find jobs? Any questions so far, or just odd thoughts that you brought in that you wanted answers to? Cool. So the areas are analog circuit design, digital and VLSI circuits, microelectrical mechanical systems, emerging devices and circuits, and RF and microwave ICs. So most of you probably have some sense of what analog circuit design is about if you've taken the first 2 circuits courses. You sort of are starting to get the idea that analog design is thinking a lot about small circuits with maybe 20 devices in it, asking really hard questions about what happens in very specific scenarios, like what if it's really high bandwidth or really high frequency. As you go down the circuits track, you'll learn that the devices become more and more real. First, you'll learn they're parasitic devices that make them behave in non-ideal ways. So you start out with your 102 or 120, the digital logic class, thinking that transistors are perfect switches. In circuits 1 and circuits 2, you eventually learn that there's a little bit of delay. And then I think in circuits 3 or circuits 4, suddenly you realize that there are more things impacting delay than you could ever hope. And the other view on delay is frequency. So if you're using them as filters, some transistors just don't work as the filters you'd hope. Digital and VLSI circuits is sort of the radically opposite perspective. We're dealing with so many transistors that we don't care about individual ones. Instead, we develop practices that lead us to ignore a lot of the small effects and let us very quickly analyze large things. So for example, my tape out that's due Monday is a 3mm by 3mm chip. So think grain of rice, and it has roughly 1 billion transistors on it. And I did it with 3 to 4 graduate students. So clearly I cannot have thought hard about any one transistor. I barely thought too hard about 1 million of them. One of the subcircuits is roughly 2 million devices, and I think I did it in a 48-hour span without sleeping. Microelectrical mechanical systems is if you think you're in the wrong major, but you've made a commitment. I'm just kidding. So after we've done all this effort to actually integrate things at super fine scales, we realize that there's significant value to integrating other kinds of devices. So the very first thing you might think is, well, what if we had sort of mechanical actuation or mechanical movement? What could we do with those? What could we sense with those? So accelerometers sense deflections in beam arms. inside the device to tell it where it's moving. Gyros have a similar thing where they're sensing deflections in beam arms to measure the rotation. And these are all very, very interesting ideas. And these are super, super relevant. So, you know, while a lot of us carry around a couple RF circuits and a lot of us carry around, you know, 3 to 10 digital circuits, these MEMS devices are the things that we often forget about. For example, a hard drive might have 2 or 3 of these in them to make sure that if you drop your laptop, it can stop spinning the disk and the disk head won't crash through it. I mean, this is back in the day when we had moving disks. Now there are solid state disks and this isn't as important. But your phones have accelerometers in them too to help do positioning and all those sorts of things. And so this is fairly important for just, you know, getting outside of the little black box. Emerging devices and circuits. So you guys have probably recently joined IEEE. If you haven't, I would encourage it. But on the IEEE front page for the last 20 years, we've been predicting the end of Moore's Law. So CMOS is over and, you know, we're never going to have better devices. One of the responses is we should build cooler, better things. A lot of the focus on this is what is the next transistor going to look like? So some of it is evolutionary, so we take the CMOS transistor and we add a few features to it. Still behaves like a CMOS transistor for the most part, but it's not. Historically, you guys might have heard of BJTs in your classes, bipolar junction transistors. So they were the old CMOS. They stopped scaling well, and they got replaced by CMOS. So we are poised to have something new, and people are actively working hard to figure that out, and there's a lot of work that goes into that. Similarly, novel circuits are something that people are interested in because, you know, digital only gets us so far. If we kind of blur the space between digital and analog, can we propose circuits that help us solve new and interesting problems? Most of the faculty and research in this area is how do I build circuits that work like our brain? So how do I build circuits informed by the mechanics of how the brain works, and can I build circuits that act like brains so that I don't need to, you know, write digital equations to describe everything that happens or run a computer. And then RF and microwave ICs is sort of going back to that very first problem with analog circuit design and then adding 2 wrinkles to it. One is we are working at frequencies well beyond what the transistor should be working at, but it still needs to work. And we need to deliver powers that are well beyond what normal transistors want to deliver, but it still needs to work, right? So if I'm running an antenna, I might need to work at gigahertz range, and I need to provide powers in the watt ranges, but transistors don't like doing that. It's sort of unfortunate, right? The total power budget for my 3mm by 3mm chip is maybe 2 watts, but in RF I need transistors that transmit in the watt range. So this, you know, there's a whole bunch of interesting questions there, and it's a lot of fun. So if you were wondering how it is that we're going to get, what is it, 5E, the new 5G, there we go. Yeah. If you're wondering how that's going to work, these are the folks that would be able to answer it. You know, what happens as we push frequencies higher and higher, both in terms of the waveform, the antenna, and the circuits. Cool. So does this roughly make sense how the areas are divided? Did anybody have questions, or did it seem like I didn't really explain correctly? Because this might be one of the fundamental questions you might want to answer is, do we want to focus on one over the other? And so this is a good place to stop and ask that question. Yeah?
So if I want to focus more on like circuit boards, which area would you recommend?
So you want to learn a lot more about PCBs. So, honest answer, there's a weird problem. Nobody teaches a class on PCB design. The reason, so there is one class, Sean Jordan at the Polytechnic School has an embedded systems class where as a part of that they actually manufacture and design their own PCBs. So if you're really interested in learning about that, that might be the thing to go do. He might walk you through that. Part of the reason is that PCB design is relatively easy. It's not that hard. You kind of pull up the tool, it's Microsoft Paint, and then with all the information that you have from EMAG 1 and linear circuits, and you know, if you draw a line out of wire and it connects 2 pins, the pins are connected, that is 90% of what you need to know to build a successful PCB. Okay. So the next thing you might say is, well, I really want to know how to make PCBs. Like I want to build really good ones. Then I might talk to the RF and microwave IC folks, Because you can imagine that when they build a PCB to test their stuff, they actually think really hard about the electromagnetic properties of the traces and what's going on. If we had more digital faculty, we might have like a digital system design class that kind of looked at some of those issues, because there are high-speed I/O design challenges where I'm trying to build matched things for, say, a DRAM bus or a PCI bus. But again, even that's kind of easy. Like me and a buddy, when we were your guys' age, we just got it to work by reading the spec, trying a bunch of times, and then it worked on our second try. It wasn't great, it wasn't perfect, but it's not really there. And I don't think we're going to have a class that covers it, so that if you really wanted to get PCB experience, you'd want to follow up with the faculty and go, I would like to volunteer for research, and my goal in doing that is to learn about PCB design. And maybe they'd be able to help you, and maybe they wouldn't. I've gone the rounds on this because I do test chips, so I package them and I need to put them on boards. And sometimes it seems like it's a good idea to give it to a student, and sometimes it seems like it's better to eat the $1,000 and have somebody who knows what they're doing design the PCB for me, because I don't want to have a grad student do it, and I'm not sure I could trust somebody randomly off the street to build it for me. But the RF guys do need to build their own because they don't trust the guy that you'd pay $1,000 to do it, right? So maybe they'd help you out there. But yeah, that's a hard one. I think in terms of if you wanted to have practical experience doing that, it's pretty cheap to get them manufactured. So if you're willing to blow $100 just trying something out, you can design something, send it out to China, they'll send it back. That works pretty well. Capstone is often a good time to kind of target that as one of the things that you want to do, and I think you can ask the department for money as a part of Capstone to cover some of those costs. Sorry, that was a long and involved answer, but hopefully that helped. And then you had a question?
Yeah, I was going to ask about RF and microwave. Mm-hmm. So I see the word, but I don't quite understand the meaning.
So if you think about the time delays that you might have been talking about for transistors, you might have been talking at the rates of like microseconds, or if any of you have been building op amps and built a low pass filter, it may have been filtering everything below like 10 megahertz at the most, probably sub megahertz, because it's really hard to get those things working. So those relatively slow speeds. And then when I think about the slews in my high-end circuits, right, I have edges in my design that are 5 picoseconds. So I think that's order, 10, 20 gigahertz. It's sort of something you could easily build without it getting lost in the way, but I don't supply any of the current you need because the currents are well into the picoamps. But somehow these devices need to work at hundreds of gigahertz and provide watts of power. And so it's sort of, one way to view it is that if analog circuits is worried about asking questions about parasitics and does it really work, and what happens as we really consider this in detail, and digital sort of scales that up 1,000 times in count, RF and microwave scale it up hundreds of times in terms of frequency and power. So one way to think about this is, I think you all learned about gain bandwidth constants and amplifiers as a part of the circuits too. So there's a hard law in amplifiers. So you all learned about amplifiers, you learned about op amps, you learned feedback will let you pick very specific gains. So there's a weird problem, is that there's a gain bandwidth constant for the little black box that's the op amp. So somebody will say something like it is a 100 megahertz gain. So the bigger I make the gain in that amplifier, the lower the frequency it can put out. The lower the gain, the higher the frequency it can put out. And so if I want that little black box to have a higher gain bandwidth constant, I need to do a lot more work. These folks deal a lot more with discretes. And we have really good faculty in this area too. So Jennifer Kitchen, Bertan Pagalagu, Saeed Z, we'll talk about him in a bit. They all work on this. I suspect this is where you might ultimately end up if you were interested in analog, is that you wouldn't focus specifically on analog itself. You would try and take a few RF and microwave IC classes. I hope that helps a little bit. Cool, cool. So we have lots of folks. So there are those of us who focus mostly on digital and VLSI. So I'm Brunhaver, that's Kao, Chakrabarty, Fan, Ogros, and so. Fan is relatively new. He does neuromorphic stuff. Ogros actually contributed a lot to Xeon processors, so he's good at architecture. So does some neuromorphic stuff too. We have some good analog faculty who focus on things like power. So how do I do on-chip power distribution and on-chip power regulators? So that's Dr. Bakalagu, Kiai, and Ozev. Emerging devices and circuits. So Dr. Ali, I think he was the director of the flexible circuits place for a while. And Dr. Barnaby, he has some cool memristor-based circuits that work really well in outer space. MEMS and bioengineering, Dr. Che is working on some novel sensors to just kind of help with medical applications. Dr. Christian has a really cool project in India building medical devices very cheaply to detect the occurrence of disease, and also has some neat animal experiments that are going on as well. RF and microwave ICs, we have Kiai, Kitchen, Trichopolis, and Z. I still haven't quite mastered that one. And they are all doing great work. Kitchen actually worked on satellites, building the RF circuits to go into the RF comms. She has a cool project right now looking at machine learning to design those circuits, and so neat sort of crossover between something that was traditionally a computer science field and something that is very analog, and it kind of shows you the trends for where we're headed. Trichopolis has some neat terahertz range sensors that kind of try and image things behind walls, so very tiny antennas, very high frequencies, very interesting problems. And Saeed similarly works on some of the circuits related to working on those terahertz things, though they work on separate projects, though they do collaborate as well. So these are the people, and you might have encountered them already on your way through circuits classes, and you will certainly encounter more of them along the way as well. Oh, that's a good point. Yeah, so most of us are on the 4th and 5th floors of ISTB4, which is kind of weird. So it's the kind of south and east of here. That's cool stuff. The big idea was that CC is in that building as well, the folks who do some space exploration work. And so many of the circuits faculty focus on circuits for outer space, and the idea was we should be collaborating with them. And I think that's working. I have not succeeded in that at all. Oh man, so circuits are in everything, right? Except for the table and even some tables, right? Circuits are in everything. Most of you are probably carrying around at least 4 to 5 digital processors. A lot of you are carrying around at least 3 to 4 separate RF circuits, right? So if you have a phone, it has one discrete RF circuit just to do the cellular network. It has another RF circuit to do the Wi-Fi. It has yet another RF circuit to do Bluetooth. I think mine has yet another RF circuit just to do FM radio, which I really appreciate because I'm still a little bit old. It's sort of everywhere. Cars have hundreds of processors everywhere, and then since they're worried about them breaking, they often have like 3 copies. So there's like 3 processors in charge of your brakes each. So sort of high levels of craziness, and then it's getting worse, right? Because now everybody wants multimedia things in their car and all that, and so you have roughly 2 or 3 cell phones worth of technology in the car to do multimedia stuff. Satellites are more or less, a little metal foil around a ton of electronics to do work. Biotechnologies, right? So a lot of the stuff that people are building, just, for example, cochlear implants, which I think that's a picture of, how do I restore hearing to people? That's an electronics problem. And I think all of us are sort of dealing with this one way or the other. Is there any sort of application that you folks are specifically interested in that you want to talk about how it's related to the circuits pathway, or something you're fundamentally interested in how it's related to circuits? My pathway into circuits was from computer graphics and rendering.
The heartbeat? The heartbeat one?
I'm sorry, I'm not quite catching you.
You say the hard processor, or what's used in the processor?
So the biotechnologies for the heart, or pulse makers, or pacemakers. Sorry, my words have left me today. So pacemakers are a really interesting circuit, right? And it seems really simple because it's just a clock. You set a time on it and it goes ping, ping, and the little electronic shock is enough to keep the heart steady. And this is how you help with arrhythmia or people whose hearts are failing and tend to slow over time. It sort of just stimulates them to keep them going. But it's sort of a really interesting design problem because the shock can't be too strong because it might damage tissue. It can't be too weak or it won't work. And this is the normal like Goldilocks problem that you guys hear over and over in engineering. But there's also really interesting implications to dealing with people, right? So we got to get a battery in there so that it'll last a long time. Because people aren't that interested in going and having open heart surgery every year to replace a battery. Ideally, you'd put the pacemaker in once and it would last 50 years. You know, the patient would expire for other causes before the pacemaker ever came up. Can you think of an electronic device you have owned and operated for more than 7 or 5 years? I mean, those of us who are particularly fastidious have laptops that'll last a decade, but you know, your peers will keep laptops for 3 years and chuck them. And you know, those of us who are really good at taking care of things and being thoughtful and good with money, right? We can get a laptop to last a decade, but normally people don't do that. And the laptop bomb is supposed to last 7 years. So a laptop lasting about 10 years, sort of in the statistical range that this can happen. In fact, most of our electronics are only designed to last 3 to 7 years at all. So that's kind of weird. And then the battery needs to last that all 50 years. So I need a compact battery source, but I also need to efficiently use that power. So these are sort of wonderfully insane problems. And then people love to cheat, right? Because I just gave you what sounds like an impossible problem. Do you know how you beat impossible problems? You reject the basic assumptions of the problem and then figure something else out, right? So maybe we can transmit power into the circuit externally through RF. And then the circuit doesn't need to be as good, it'll last a lot longer, I can recharge it. But now I need to pump power into somebody's chest with the moral equivalent of a microwave. That's kind of disturbing. One of the, there's an organ in the male body that always gets cancer. You're supposed to go to a proctologist when you're 40. What's it called? Prostate. Excellent. So prostates get cancer and we need to remove them. It's something that men are very sensitive about when they get older because there are implications. So you want to be very careful when removing it, and also it's a very common for older men. For example, my father, grandfather, and a lot of the older men I know have problems related to their prostate. It's sort of just, you hit that age, you're going to have a problem. That's life. One of the ways to remove them is microwaves. Is basically you focus microwaves right on the organ, burn it, and it gets absorbed by the body. I have a buddy from my undergrad whose specialization was building endoscopy equipment to help remove scar tissue from damaged joints. And basically what it was a plasma torch attached to a vacuum. And so he'd run the endoscope in, generate a very, very small plasma source to burn the scar tissue, and then there was a small vacuum to burn it out. And so the problem they ran into, so the design challenge that he was hired for was that the original designers built a plasma torch that would simultaneously burn the end of the torch and the flesh, and so it was only good for 5 uses. And then he built a version that was good for infinite uses because it stopped burning the end of the torch. So there's tons of really fun problems that sort of interact with, you know, the very limits of what we can do in circuits and human beings that need help. You know, and I would encourage you that if you're all interested in this, I think Dr. Blaine Christensen teaches a really wonderful class, does really awesome research, and has a big lab where you could get tons of mentorship in this area. And I just adore her. She is awesome. Cool. Any other questions about applications?
Robotics?
Robotics. So, a little bit. it's going to take some stretching to get into robotics. So one thing that happens a lot in robotics is there are MEMS devices everywhere to keep track of what's going on. So one of the things that people are interested in is dead reckoning. So that's not an appropriate story. So GPS fails every now and then, right? And you need to know where your car's going. So your car's going through a tunnel. There's no GPS. How does it know that it's still moving forward? Well, if I integrate the accelerometers, right? So you remember back to physics 1, I can just sum up accelerations. That gives me velocities. I sum up velocities. That gives me change in position, right? So I could do that in a computer with an accelerometer. So this is something that occurs a little bit in robotics. So when I built like a self-flying blimp for my capstone, don't worry, it didn't actually self-fly. The bar isn't that high. We put 5 or 6 accelerometers on it to do the dead reckoning. We put 2 or 3 gyros on it, and then a lot of this was the controls that came up with this. And we spent a lot of time trying to figure out how the circuits worked for this, because in those days you couldn't buy a digital sensor. What you got was an analog sensor. You were responsible for building the analog amplification pipeline with all the control gain, and then reading it into an ADC, and then figuring out what it actually meant. These days, they'll give you ADCs you can read over SPI, and it's a beautiful, beautiful thing. You just have to think a lot less. On the other end of robotics are these sort of application-specific computation problems. So one of the problems I looked at in grad school is called the localization problem. So I have a robot with cameras, and it's wandering through a building. Can the robot remember what room it's been in just from the cameras? That seems like an easy problem because all of us do this constantly. But remember, an image is just 3 letters organized in a matrix. 3 numbers organized in a matrix, right? Like the computer doesn't see things, it sees numbers. So you have to teach it how to see the walls, and there's fun math problems built into that. And so some of the work that I do, Dr. Ogros does, and Dr. Chakrabarty does, looks at, can I tailor my digital designs to focus on these kinds of problems? So right now, Dr. Chakrabarty and I are looking at how do you build really good radios. I have another project looking at image processing problems. And peripherally, we're interested in some of the controls problems. So in that sense, there is a relationship to robotics, and that robotics are going to need some of these things. But there's probably not a specific class that'll go, here's a robot. It's just sort of all germane to robotics. Cool. Any other questions about applications?
Automotive, you can talk a little more about the automotive.
Yeah, so automotives are robots. That's where people are headed. So almost all cars now actually have a radar on them. So they have 2 or 3 radars on the front and 2 or 3 radars on the back to do the collision avoidance thing. So radar is kind of a fun problem because it gives us our RF circuit. Then it needs a digital processor to actually figure out how to interpret these RF signals into what's going on. It needs some control systems to figure out what to do, right? Because now there are 3 or 4 people that can volunteer information for how the car can be controlled beyond the user, right? So that thing that does the collision avoidance slams the brakes. But it needs to slam the brakes in a way that doesn't disrupt what the driver's doing, right? Because if the driver is turning at the time, right, that could be really bad. It also needs to do it in a way that doesn't cause a skid, right? So the anti-lock brakes is kind of this really neat classical controls problem. There are custom circuits that implement that directly because that decision needs to be fast and bulletproof. And so those are all baked in. A car is literally a collection of, hundreds of MEMS sensors, tens of RF systems, right? It has classical radios, but it also has satellite comms. It also has Bluetooth, right? As most of us would like a car with Bluetooth so our phone can talk to the car and they can be happy friends. There's just everything in a car. And then the fun part about cars is, did you know it's very upsetting when cars get in accidents and people die? And the electronics are related to that a good bit too. So it would be bad if it was the electronics' fault. Because if it's the person's fault, we can blame the person. If it's the car's fault, that's really upsetting. Right? We'd always like to blame a person. So cars have a different design standard than normal electronics, right? So if your cell phone powers off randomly, you go, that's annoying, right? And that happens, what, once every 3 months? If you've noticed it all, you might have assumed it's your fault. You might have assumed the battery died. You may have not even been present for it happening. You just came back and the phone was off. And you have no idea, right? But if your car had a critical system that randomly shut down, that would be a problem, right? Especially if that system was the power steering system. And all of a sudden you were responsible for, going 50 times harder than you did before. If your family has an old truck, that is the experience. Worse than that, it can make mistakes. Right? So there's a good set of the, Toyota makes a car, it's, I hate, it's kind of ugly. It's the Prius. Yeah, so some of the Prius accelerator accidents boiled down to an error. A particle from outer space randomly collided with the processor. The processor made an incorrect decision and accelerated the car into a wall or another car. It was incredibly difficult to root cause these things, but they eventually did. And it happened a statistically significant number of times. So how do we design circuits that are immune to these problems? So this is a question that myself, Dr. Clark, who's not really here anymore, but Dr. Kitchen, Dr. Barnaby all worry about quite a bit. And I think there's a new faculty who also worries about this. He's not in this area. Dr. Sanchez, Yvonne Sanchez, does this sort of work as well. I'm more design focused. Sanchez is more device focused. Barnaby's more circuit focused. But yeah, cars are kind of wonderful. And then there's just normal failures that happen. And so the reliability requirements are a lot higher. There's an apocryphal story about Intel considering going into the car market and deciding that it was not worth the pain and suffering. So car manufacturers also design a lot of their own electronics. They are fairly present at the circuit conferences. So if you enjoy cars, that is certainly a life's goal. Sort of the meta point of kind of working through this is that if you enjoy something, it is probably circuits related, right? So I had a bunch of friends. My peers in graphics actually joined because of photography, and they got sucked into circuits because they really enjoyed the circuits involved in photography, right? So there's a digital sensor. That's a circuit problem. There's a control system and a processing engine. I really enjoy those problems. And so, it's sort of everywhere. Circuits is like learning to paint, right? Is what you paint is kind of up to you. Thoughts, concerns, hopes, dreams, desires? Cool. So there are classes. I think you're required to take them. I think you're required to take the white ones. I don't know anything about advising or what rules you're supposed to follow. I just know there are classes and that the only one you have to take is 333. I'm pretty sure because I taught it. What's that?
334.
And 334. Cool. And then they need to take like 2 of the other ones?
Right.
Cool. I was in the neighborhood. Yeah, I'm really bad at reading rules or remembering them. And it kind of works out because it's not my problem, it's kind of your problem. So 333 is a weird class. A lot of you might be interested in RF or analog and are entirely upset that you will have to go take a class that is digital circuits, and not only is it digital circuits, but is a class where you will never see a circuit. It is a weird thought, right? So for the digital folks, they go, this makes perfect sense. So here's why you're taking it, and hopefully you have an instructor like Harton or Abraham who takes the time to kind of work through why we take this class, right? So one is, if you're doing digital design, you have to learn this. This is just hard and fast what you got to do. And if you're gonna build anything with an FPGA, this is gonna be involved. And so it ends up being practically relevant to a lot of real systems just getting work done. So what about from the analog end? Why should you care? Well, one is, what the class is actually trying to teach is debugging. And how do you think from a pre-design scale to a post-design implementation? So how do I make a plan, and then how do I execute it? And then when the plan doesn't work, because it's not gonna work, how do I fix it, right? And so if you've been in the lab in Circuits 1, and you've been building the circuit for the cookbook, and it doesn't work, what do? And that's what you're learning in 333, is how to do that, right? How do you work backwards from a problem and solve it? Unfortunately, we can't really give you a flow chart for debugging, right? Nobody has sat down and systemized debugging to a point that we could teach it as a memorized skill. It's an experiential skill. Some of it's just a resilience problem. You have to have done enough of it to realize that this is not an accusation of you, right? When your circuit didn't work in circuits 1, it's not because you failed. It's because this is the reality of what we do, is you put something together and it just doesn't work. It's almost impossible to build a perfect plan to get something to work on the first try. And if you did that, you would spend so much time doing that, you'd be so far behind the person who just was willing to fail. And so this is sort of what we're teaching. And there's ideas in that class like how to test things. So how do I know that my thing is broken, right? How do I build tests to more thoroughly examine it? And so all of those designs are portable to analog, portable to RF. And so that's sort of why it's at the front end. And so even if you never again write HDL, hopefully you're looking at that and going, okay, when I do my analog design, I have more obligations than just drawing the schematic. I need to build tests for that schematic. What do those tests look like? Right? How do I organize those tests? What happens when the tests don't work? What does it mean to just go beyond the basic test that most people do, right? Because in class, when they ask you to design an RF circuit, they're going to give you one waveform and then say, does it produce one waveform on the other side? But in reality, that doesn't cut it, right? You're going to need to do a little bit better than that. And so 333 kind of provides some of the culture background for that. So hopefully you feel a little more engaged if you're already in it and we're wondering why is this happening to you? Otherwise, it is just basically useful. And then, the broad theme, 334 to 335, is that we keep lying about how the circuits work, and then in every class, we make it worse and harder. And so the left track is basically, let's keep figuring out how disgusting transistors really are. That transistors are awful, and that what you thought was one really simple device is actually, compactly describing 20 or 30 sets of passive elements and 3 or 4 dependent sources, and you're going, oh wow, this is truly hard and bad. And some of the tricks for dealing with, now that I have a complicated model, how do I bubble it back up into things that I can actualize about the circuit? The right side is a rejection of that idea. So we're just going to say, yes, we know everything is gross and awful, but here are a few simple tricks to live your life by. If you follow these rules, you can ignore all of the gross, awful things that happen. That's great. Then we scaled it up and went crazy. So VLSI is, now that I have systems with billions of transistors, I have new problems that are gross and awful. How do I deal with those problems? And so they complement each other kind of well. So I think roughly the organization here is that right-sided stuff is sort of digital, left-sided stuff is more analog, and then there's a middle track on MEMS, this 538, 598. There are always new 598s and 498s, so it's always worth kind of taking a quick peek to see if any of them are relevant to what you're interested in, especially as you're kind of getting to the terminus of your program. Let's see, so A to D is how do I take analog signals and make digital things out of it? It is actually a really fun problem. I enjoy spending lots of time trying to figure out how I build really lazy ones, because again, a digital guy hates thinking about how things work. RFIC is how do I build integrated circuits for RF? Oversample converters, I have no idea what that does. Switch cap is, you might think that one way to build an analog signal out of a digital signal is to use a resistor network. Bad news, there are no such things as resistors in integrated circuits. You're not allowed to have discrete resistors, they're gone. So I have to build everything that I used to build out of resistors, out of transistors. Transistors have capacitors on them, at least our CMOS ones do. So if I build capacitor structures, I can re-implement things that look like voltage dividers. And that's what that class is about. And given that it's a whole class, you can imagine it's kind of complicated. Though I have a theory that it's not that complicated if only you just cheat and make it an easier problem. Bioelectronics, I think, is Dr. Blaine Christensen's class on that topic. High-speed serial links is this problem where I need to send bits between 2 chips on a board. This is a really common problem. So if you've ever built your own computer or broken up in your computer to replace things, you notice there are little slots with RAM on it. And they talk to your CPU. And they need to communicate at really high bandwidths. So, billions of bits per second. But those links don't want to go very fast. So if I'm lazy and I don't do any work, I might be able to get 100 megabits per second on one link. But I need to get gigabits per link. So that 3 orders of magnitude difference is that class. And it's a little bit digital, it's a little bit coding, it's a little bit analog, it's a little bit E&M, and this is sort of the theme that happens as you progress in both these programs, is that you start to care a little bit more about E&M, and you start to care a little bit more about some computer scientist-oriented things. Symmetric VLSI, so it turns out there's this awful thing. Some of you may have had this experience. You go and you try on clothes at the store. Same size, one fits, one doesn't. That's manufacturing variability. So you might think, well, that's because people make clothes. No, it's because it's built. There's just randomness in the universe, and entropy is awful. Turns out entropy is also in our devices. So when we build a transistor and you specify width, you actually get width plus some noise. That causes problems. If you'd like your devices to match, because your widths are very, very important to your circuit actually working at a very specific frequency, you need ways of tricking it to do that. Symmetric VLSI is a class taught by, I think, somebody who works locally to work through that problem. Like, how do I lay this out to mitigate most of those effects? And then the other is RF amps and transmitters, works through that. There's a CSE EE 518 synthesis. Is that Sarma's class?
Which one?
The CSE EEE 518, Sarma Vidula.
518, I think that's a cross list with another department. Yeah. So another department's faculty teaches that. Our faculty do not.
Cool, so I think that's Sarma Vidula's class. The big idea is that, remember how I said we didn't actually describe what the digital circuits were, we wrote a language? That's the class that talks about the algorithms of how I take that language and actually make circuits from it. And then I think he does the fun thing that is, what if you didn't write HDL? What if you wrote a much higher level language? How do I convert that into circuits? So that's pretty interesting, and he covers some cool thoughts. It is a very computer sciencey oriented class, so it's, if you didn't feel there was enough programming in your circuits, that is a wonderful thing to go do. 625 is Advanced VLSI. So that's the title she picked. What the class actually is. So this is Dr. Chakrabarty's class. It is, if I really liked digital signal processing and I wanted to work through the theory of implementing the circuits to do digital signal processing, that is the class to take, right? And so if you learned about FFTs or convolution and thought there's no way hardware could ever do this, this is the class that should answer that question. No, that's 526. Sorry, that's VLSI architectures. Advanced VLSI 625 is, after 525, we've learned all of the awfulness that exists in the universe. And then we realize that as digital designers, we have to embrace our inner analog designer to get stuff that we actually want. Specifically, if I want memory, I have to master enough analog design concepts to actually make my memory work, which is scary and awful. But it's one of the best classes I ever took in my graduate program. I'm not sure that you guys have the bandwidth to take this, but this might be a fun thing to try and shoot for if you're going to do a 4+1 or an actual MS thesis afterwards. I think this has not been taught for a long time. This might be the first semester it's taught. Did he actually do it this term?
Clark? No.
Not, Clark's gone. Dude from ARM, maybe he's retired.
Security?
No, he normally covers 525.
David, Reginald.
Reginald, yeah.
No, I don't think he's on
I
625.
don't think so.
Cool, because he has the slide deck and he's been working on figuring it out. And
Oh, no, okay.
so this is sort of a Clark problem. Like, so there's, and I love him like a brother, but yeah. And then Reginald's going to be doing his best.
Cool.
So the first version of the class is going to be awful.
That happens.
So if you enjoy seeing when faculty are a mess, that might be an opportunity to see that, or just come visit one of my classes. I have no idea what 598 modeling is. 598 computer architecture is my class where you took 333 and you went, yeah, this isn't enough. I need more of this on full blast. That's the class. I'm going to update the class massively. So Cheryl, I'm going to ask for a new course number and a new course name. Is that going to irk you?
I would love that.
So I'm going to change it to an actual 598 so that people don't have to do the 591 thing.
Oh, okay. Oh, okay. Send me an email.
And then we'll cross-list it to a 498 so they can take it to credit.
Can we do that?
Well, I'll.
There are no rules. But yeah, I'm going to make it more of a service class than it is right now. Because yeah, there's no FPGA class in the university. So we're going to shift it that way to help out the signal processing guys and the controls guys. Because they have nowhere to send their grad students. And they've been sending them to me asking really weird questions. And they don't want to take my class on architecture. Anyway, so that's sorry. I do a lot of things all at once in my head. There might also be another 598 computer architecture taught by Dr. Ogros, which is if you've ever wondered what happens when you put multiple cores together and how I get them to talk together and what the implications are, that is that class. And Dr. Ogros is an awesome guy to go take that from because he was actually one of the architects on Xeon processors for building that interconnect to put processors together. So he is an actual authority, not on like academic authority, but practical professional authority on how this works. On my current projects, he owns that interface. So he is the guy that I go, great, on a project, if he's in charge, we're going to be fine with this problem of how processors talk to each other. Because my domain is roughly, how do I not do that work, or how do I build accelerators to make math fast? Let's see, what else is missing? Jason, so Dr. CO teaches a class on neuromorphic inspired computing. That's probably worth taking. Neuromorphic inspired computing is this idea that how do I build computers that work like brains and that sort of thing. Cool, any questions about classes? Cool. We had new faculty. So George is in year 4, so we should update that. Saeed is pretty new. I think maybe last year or the year before, and Delying is also new. George does terahertz imaging, Saeed does terahertz RF, and Delying does neuromorphic inspired circuits. So how do I build circuits that look like neurons in the brain? And he has a big focus on how do I do that in a memory? So how do I make a computer memory look like neurons? And it's all very good work. So what's going on in terahertz circuits? Well, one weird idea is that you learn about radios and you learn about light, and you're told they're the same thing, and that they all have frequency and wavelengths, but they're different things, right? Because you can see light. Light makes pictures. And you can't see the radio. But they're the same thing, right? So terahertz is right in between. It's almost the point that it's light. Not quite though. And much faster than normal radio. So you can actually use it to make pictures, right? And so it looks like a camera with a lens. I mean, it's not the same sort of glass lens that Copernicus might have used. It's something much more interesting because it needs to mediate the terahertz waveforms. But it's still sort of there, and it can produce fairly interesting images. And he's worked on a lot of medical applications to figure out like how I would use this in medical imaging. And I think he's also took a pass at sort of security-based angles. And when you manufacture this in a VLSI way. So you actually build chips to do this because the antennas are that small. I mean, not transistor small, but still relatively small. So I wouldn't etch a PCB with these antennas. I actually need to build the integrated circuits. And then, a lot of his work, since it's focused on the antennas and the tail end of the RF, he needs to spend a lot of time doing testing. And I think he actually teaches a 598 on some of these testing techniques. Oh, cool, new slide. So this is Saeed's slide. So how do I do millimeter wave and terahertz? Some of these ideas are maybe I could do really good imaging to see if people are carrying things they shouldn't be carrying. Some of this is how do I do really good comms. One of the interesting things is that maybe in the terahertz range I could do simultaneous communication and imaging, so I could actually see people in the room while doing the imaging. This is going to be part of how we get really high bandwidths. Right, so if you're interested in have your data rate, megabits per second, right, the trick is I need to cut huge chunks of the spectrum in order to get those bandwidths, and so terahertz might be how I do that. Dr. Kitchen works on power efficient systems and circuits, so how do I make smaller, more integrated, more efficient things. Some of this is focused on how to do satellite stuff, so she has SATCOM transceivers in there. And how do I do power management? And she has some neat remote sensing things that she does as well in order to have low power circuits manage high power circuits. Neuromorphic computing. The big idea here is that GPUs are sad. GPUs and FPGAs are sad in terms of the amount of energy they take to do things that we do relatively easily. So maybe if I just built the circuits better or organized the transistors better, I might be able to get where I'm going. And so this is sort of his pitch for that. So I think this is the general pitch. And this is Dr. Sio's work. So this is a cartoon of something called convolutional neural networks. So this is one of the big innovations in the past 10 years in neural network applications to image processing. So this is how Google did the daydreaming stuff on YouTube and that sort of thing. This is what's been enabling self-driving cars to work. This is really great. And so he's kind of all consumed with how to do that. So let's see. There's a lot of stuff going on here. I've touched on a lot of it. Where do we find jobs? So let's see. So I worked at Intel for a while, interviewed with Raytheon. We have students that go to both those places. I think somebody from Intel was saying that if they look at the population of students they hire, they pull the most engineers from ASU. So they went and ranked it and said, what school do we get most of our engineers from? Or what is the largest population of engineers? And it was us. Raytheon does a bunch of things, mostly military contracting. My experience with them is radio and radar. Honeywell builds similar things and also focuses on some space stuff and some sensors. General Dynamics does defense communications, like how to build really good radios. Boeing builds aircraft. Sometimes it works, sometimes it doesn't. IBM, the oldest computer guys, they still build computers, believe it or not. They have some really interesting computers that sort of build what we call the high performance computing space. So how do I build a supercomputer? If I still want a computer that fills multiple rooms, they're some of the guys that still do that stuff. Freescale Semiconductor do semiconductor integration work, so they build novel devices. Microchip are a local company headquartered in Arizona. They do lots of things. If you've ever used a microcontroller, it might have been from them because they build pretty good ones. Orbital Science Corps does aerospace work, and as a part of that, they build the integrated circuits and RF systems for that. Where do we find jobs going on? We work at some of the best companies in the world. So I've worked for NVIDIA. Instead of coming here, I had an offer to go to Google. Some of my students are trying to go to Google, and some of our students do end up at Google. We have relationships with Facebook, and some of our students go there as well. Cadence Design Systems is the company that builds the schematic capture tool that you might use. And they do a lot of stuff just beyond writing software. They actually do design work. Intel again, Qualcomm builds the SoCs that go into most people's cell phones. So they do tons of stuff. They do the RF, they do the processor, they build a lot of it. And then I forgot what Burns & McDonnell is, but it's a very good company here. Where are you guys going? You're going to this list of places. These are all pretty good places to go. We have a lot of jobs in Arizona. This is sort of a good point. We generally are kind of focused in kind of the southwest, and then the northeast, and then peripherally in Florida. So most of our jobs are sort of California, Arizona, Texas, and then there's a good number in the Massachusetts, New York area, with Illinois being an outlier. The reason there's something in Illinois is that there's huge aerospace headquarters near some of the Air Force bases out there. The reason there's in Ohio is that where Wright-Patterson Air Force Base is, where the Air Force does research. And so there are a bunch of companies that have immediately put themselves right next to that. The reason Michigan's doing really well is they have a really great EE program. And for some reason, those people want to be cold forever. So when they start a business, they start it right next to the university. And similarly, that's why California is doing really well, because they do that. And we're doing really well here, because when you guys are done, Arizona's a great place. That's why you're here, hopefully. And so you might want to stay here for a long time and start a business here. I think there was a recent report saying a lot of the economic growth in the area could be directly attributed to both the students here and the work done by faculty and just some of the programs done by Michael Crow. And so that's certainly some of that evidence. That's something to keep in mind. One thing missing from this, for some reason, is Washington and Oregon are also places that people work. It's kind of interesting. Yeah, because Microsoft is in Washington, Oregon has a really huge Intel organization, and then because Microsoft and Facebook are in Washington, and because Intel's in Oregon, there are a bunch of smaller companies, satellite offices, that try and poach employees from the big sites. Okay. So sorry to hold you 5 minutes over. If I am holding you for the thing that you need to be at next, like class or something else, please run. I'm happy to stay for 10 to 20 minutes to answer any questions you have. Yes?
I just have more of a personal question.
Sure, I love personal questions. Yeah, I'm sure everybody wants to know. Just ask me. Or is it personal to you?
No. I hate coding, so I'm NE333. I love circuit design. What do you suggest would be a good time? I can do it. I hate coding.
So the way that I learned this a really weird way, because when I took my version of 333, the guy who was supposed to teach it was sick, and they brought in an emeritus faculty who had never actually written the language, and then decided that he wasn't actually going to teach the class. So I had to teach myself how to do this. And the way I roughly learned, and this is the way that a lot of the Intel folks think about it, and the way that I try and teach the high-end class, is that Verilog isn't really a programming language. It's a net listing language. So you aren't writing the language that implies this. You aren't writing a language that gets translated into the circuit. You're more or less writing an H Spice Netlist in a very strange way. And so that's sort of how I got into it, was I went, oh, okay, when I want this module, I'm actually placing this module. When I want an AND gate, I'm actually placing this AND gate. And so from my perspective, that's sort of how I sort of realized it was circuit design for me, because that was the input medium for that. And it was actually a lot faster than drawing schematics, because I can type very fast. And so that sort of worked well for me. Going forward, no matter what career you're in, and this is sort of a hard blanket statement, even if you decide you're not going to work in circuits, you will have to learn how to program. Period, full stop, you gotta have to learn it. Every job has programming. If you do not know how to program, you are going to have a very hard time keeping a job. It is how it is. So even if you decide, no digital for me, I'm gonna do analog because I really appreciate the beauty that is math and circuit design and focusing on hand-drawn things. Turns out that every time, so the lab I used to be in for my graduate program was half digital, half analog, and half bio. The reason it was halves is that our advisor had 50% more students than he really should have had. So that was a joke, not a very good one. So the analog students spent a lot of their time writing programs to analyze their circuits, because the design part was kind of easy, but proving that it was going to work was hard. And then when they actually went to go manufacture these circuits, there was a little bit of work in just sort of the inputting that circuit into the tools to get it manufactured, but there was a lot of work writing the flows, interacting with the flows to actually check that the circuit was legal. So for example, one of the things you're going to learn about are design rule constraints. So when I use lithography to manufacture things, there are rules like 2 pieces of metal can't be too close together. Now, you would think it's the honor system, right? Is we're just all going to agree that we're all going to follow the rules, and when I submit the circuit, they'll build it. Problem is that if you break the rules, not only does it break the chip that you're on, it could break other chips. Or the story I heard recently about why people are mad at people like me is that it could break other projects like days later. So I contract through DMEA, which is a government organization that sponsors tape outs at leading foundries. So I put in a project. So the story I heard from them is that somebody put in a test project as a part of a military or university project, and it so fouled the machine that one of the corporate customers who was on the trailing run was delayed a month. So that foundry is mad at us, just in general, universities and military designers, just because in their view of the world, it's us against them, and so it's the foundry versus all you people. And so, yeah, we got to run those decks, and those decks are complicated, and you got to write little scripts to parse the stuff that comes out. You got to automate it because it turns out there's like 6 checks I'd need to do. One of the checks is, did the thing I draw for lithography and manufacture match the circuit I asked for? And then if I'm doing analog stuff, I might have implied certain passives to exist, like I might have actually drawn the metal in a funny way to imply a resistor. So I lied, you get resistors, but you want to make sure that resistor is there and then it's the right length, and so you got to write all the checks to do that. So there is a good bit of programming involved. It's not crazy programming, right? Like nobody's going to ask you to solve some really hard math problem. It's very procedural. And, the hardest they might ask you to do is to go grab a text file, look for a specific string, put it into a spreadsheet to make it easier for you to read out the reports, that sort of thing. Dr. Ali and Dr. Harton have the Python class, and that might give you a good idea of where to go and that a lot of the base skills. Unfortunately, Python has not yet taken over in the integrated circuit world. Everybody's still using Perl, but Perl is just Python with extra symbols. And to be honest, as the old people leave and the young people show up, it'll switch. So you guys are probably right at the perfect moment where showing up knowing a lot of Python might induce groups to change their culture. In my lab for our tape out flows, I said I wanted Perl. I came back a week later, everything was in Python, and what am I going to do? But yeah, programming is kind of important. It's often how I solve a lot of my problems. So I periodically have been given RF or analog design problems, and instead of solving it the way they teach in the class, I solve it the way I like, which is brute force iteration. Right? And if some of you may have had this experience with those labs where you're just sizing the transistors up and down, and then eventually it works. Why do that yourself when you could have the computer do it? And then, you could be awake all night and then work 10 times faster, but actually get a full night's sleep. So this programming is relatively important. So so I say all that to justify the next statement, which is, I know people don't like programming, but it might be worth spending time thinking about how you might discover the joy of programming.
It's just hard for me to find joy in it,
Oh yeah.
personally, but
Yes.
I can do it. It's not something I'm passionate about.
Yeah, there are tricks. Generally, I did not enjoy programming until I started getting to leave work at like noon, because I had gotten all my work done and there's no reason for me to be there, so I just left.
Right, so you're just saying that programming will take care of my issues that I have of me spending all this time working on a problem, whereas my program could take care of doing so many iterations and seeing, oh, that's the correct width I would need for the transistor or whatever it may be. Yeah,
and really practical things, right? Like as you're rolling up a design, you need to report out on the status of the design. So what's the timing, what's the area, what's the power? And often you'll need to roll this up in a huge spreadsheet with all the components and then email it to a manager. So what I would often do, because I was responsible, somebody batched that out to the intern, and so when I was like a junior, what I did was I went, there's no way in hell I'm doing this by hand.
Right.
So I just wrote a script that did it automatically, and that year I went and learned how to do another programming language, and I finally got to read all Harry Potter. Right? Like this is sort of, it makes your life easier in ways you can't anticipate, and that's probably the point where you'll find joy, is that this is much better doing this than doing it the hard way. The other way we found joy was Amazon used to have a broken pricing tool. And you knew the pricings were consistent for about 5 minutes. So what we did was we set up watches on Amazon items we were interested in and just pinged it constantly. And then it would send us an SMS when it hit a price we were interested in, then we'd buy stuff. Because the algorithm was broken, and so every now and then it'd drop like a $20 thing to $1, or it'd drop a $1,000 thing down to $50. And so, they fixed it. But this is why people, this is how some of my roommates found the joy of programming, was that they really enjoyed the moral equivalent of couponing. Right? And so there might be something that you're interested in, and feel free to follow up with me. I have office hours 4 to 5 on Thursdays, and I don't teach a class this term, so I'm really lonely. So you can come by and.
I'll come by.
What, I've taught a class.
I'll come by.
Yeah, but I don't think I could have. It's been a really hard term.
I know you've got a lot going on.
Thanks for answering my question.
Oh, yeah. Have a good one. Yes.
The reverse question was asked last week. How would you compare and contrast this with like physical electronics, like the physical pathway?
So this implies that I know what the physical pathway is. What's the physical pathway?
352.
I don't know numbers.
What's the title for 352?
Physical electronics and photonics.
Yes, it has to do with physics.
I'll find out.
Oh, physical in terms of physics, not in terms of real. Okay.